mi novia llegue en la pieza.
Sorry.
Okay.
Recording in
No,
progress.
it's okay. It's okay.
Okay.
Just I mentioned my sentence just before the recording. It's okay.
Yes.
Okay, I begin.
Okay, Manuel.
So, as you understood, my name is Manuel Smulders, and as I was mentioning in the beginning, and as you understood also, I know few words in Spanish, but I didn't have a lot of opportunity to speak this language in the last recent years. So I'm gonna try to introduce myself in Spanish, and then I'm gonna switch to let you understand what I will try to give you as message. Así que buenos días. Aprendió español o chileno, no sé, en Chile hace 10 años, un poco más al final mira, entre 10 y 15 años al final de mis estudios, porque hizo una práctica en el tema solar. Era para baja temperatura, pero ya estaba en el tema solar. Después de eso, bastante rápidamente, empecé a trabajar para una empresa que se llama John Cockerill. Voy a mostrar más detalles a lo que hacemos, pero lo que ya pueden recordar es que es una empresa muy antigua, muy antigua, y que ha desarrollado una tecnología solar hace solo 10 años. Y cuando empecé en esa sección, en esa empresa, la sección donde yo trabajo estaba focalizada en calderas industriales. Y he tenido la suerte desde el principio de empezar ese desarrollo para hacer un transfer de tecnología de una tecnología de caldera tradicional hasta una caldera solar. Y cuando el profe Tunetti llegó ha preguntado, ¿tendrías un problema industrial que compartir con los estudiantes? Respondió que si hay una cosa que tenemos cada día son problemas. Así que voy a poder compartir algunas cosas hoy día. Mi idea es de no compartir solo a propósito de un tema, pero intentar compartir la estrategia global de nuestra sección solar y de insistir en los principios challenges. Quizá puedo acabar diciendo que soy ingeniero electromecánico. He estudiado en Lieja, en la Universidad de Lieja, en Bélgica. La empresa John Cockerill está en el sur de Bélgica. Es un pequeño país donde en esa región se habla francés, como lo notas seguramente mi acento en español o en inglés también. Okay, so I'm gonna switch and maybe I can share my screen. I wanted also to emphasize on the fact that if you want to ask questions, please don't hesitate during the presentation. I don't want to become boring, so if something is not clear, please ask in English, in Spanish, as you wish. If it's Spanish, tienen que intentar no hablar a la velocidad de la luz. If you do, I will not be able to answer. Can I share my screen? I hope yes. Okay. Let me know if you see it.
Yes, now we can see your screen.
Okay.
You can okay, yes, perfect.
Okay.
Yeah, it's perfectly visible.
I will try to stick to 1 hour. It's correct. I have 1 hour, more or less.
You can have a little bit more. It depends on you. We have time.
So it depends also on you if you have questions. And anyway, I have split my presentation in different phases. And the most interesting part, I think, is the first one. So if I have to skip the last slide, it's not a bit. I'm in charge of all technical aspects of some business unit of John Cockerill. And this business line is called Solar for CSP. This is our technology, concentrated solar power, and also thermal energy storage. So as mentioned before, our company is very old. We exist since more than 200 years. And we began our story in the frame of the first steam production on the continent. Actually, our founder is called John Cockerill, and he's the first pioneer to introduce the Industrial Revolution in Europe. The first steam machine. We did the first rail truck using steam. Then we have developed a lot of different technologies such as bridge cannons and another stuff. And currently we still have a lot of historical products, but also new products as the one I'm going to present you today. Today we have 5 sectors of activities. I'm not going too much into details regarding the other one, but just a few words maybe. So environment, mainly air and water treatment. Defense, we are one of the main provider of turrets in Europe. Industry, this is a traditional sector of activity. In the last century, when steel industry became very strong in Europe, we were one of the big actors also. And finally, services. And the one I have not mentioned yet is the one within IAM, so energy. Energy sector is divided between 2 main sections, energy solution and renewable, and we have also an after-sales department, of course. Energy solution are the historical products. We are a major provider of heat recovery steam generators and also industrial boilers. And we have more recently created a section dedicated to renewable energy. In this field, we have hydrogen production. We produce hydrolyzer and CSP and thermal storage, which is the business unit, which is my business unit actually. And the 2 last items are items which aims to make to integrate the different technological bricks of the energy sector within a single solution and optimized solution for a customer. So we have a business line dedicated to develop this kind of hybrid solutions. This is the integrated renewable solution. And finally, we have an EPC department to for instance, to take a business plan developed by integrated renewable solution, which could imply hydrogen solution and CSP products, and EPC will set up everything on site and make the assembly, etc. But basically, the 2 last items we will do it for small scale application, meaning maybe 50 megawatts, 60 megawatts. But the 2 others business units in renewables, so CSP and hydrogen, we could deal with much more higher power solution, but we will do it with external EPC because it will be huge electrical power plant, and then we will be OEM, so just a provider of one equipment. That's it for the main framework of John Cockerill, and now I'm going to to give you more clue about my technology. So we are involved in CSP for concentrated solar power. CSP is not only tower technology as you see on this picture. It could be also what we call parabolic trough. You have a mirror, cylindrical parabolic mirror on the ground, and you don't need a tower, but you cannot reach so high a level of temperature. But on the other hand, you have a very standardization of the production of the heliostats and the caloduct. So could make sense, but this is not the way we are following in our company. You can also have more exotic CSP applications, such as Fresnel application, but I'm not going to explain too much. If you are interested, please have a look on the internet. And the third technology, the most common one, is the one I'm going to present today. So the tower technology. So basically, we have thousands of mirrors around a tower, and on the top of this tower, we have an equipment called solar receiver, which aims to absorb solar energy and to heat up a fluid. This is basically the goal of a solar thermal power plant. And depending of the fluid you will choose, you will have the opportunity to store this heat or not. And if you store it, and you will have the option to produce renewable energy 24/7. Of course, this heat you need to transfer it to another cycle, such as a steam cycle, to produce electricity at the end of the day. I wanted to begin with this slide because some aspect of our technology is that it's a niche market. It's very complicated to find its place in this market, because there are very few actors, very few places around the world when you can install such application. You need very pure air, very good air quality. You need DNI, meaning sun irradiation, very good. You need a desert, something like that, because we have hundreds of mirrors, we have a big tower, so we need something where the space is not expensive. So we have a lot of constraints. And on the top of that, the technology is complex. You will reach high temperature, you will have a lot of challenges such as corrosion, creep, fatigue, everything you can imagine. So this is definitely not easy, but if you find all these solutions, we see that there is a market. It's feasible to be profitable. Since the beginning of the creation of our business, we are profitable and we are making profit and developing our technology. But of course, we do not have decades of project every year. And to survive, we need to innovate every day, every week, every month. And we need to reach targets in terms of LCOE, the electricity price. And this is what's shown this slide. A target would be to reach 5 cents per kilowatt hour. To do it available 24/7 because of thermal storage. And this is something important to understand. We have a differentiation in comparison to PV plus lithium-ion storage. There, if for a project they need more than 6 or 7 hours of storage, we are more competitive right now. So currently, what we are trying to do is decrease the price, the global price, so decrease the capex and the opex of each subcomponents of our plants, and convince everybody that it's working, consolidate our technology based on the different references we already have. I wanted to give you more clue about, but okay, it's okay. I have a few slides after just to be more precise regarding what the solar receiver is and how does it work. But as before, in 2 slides, I'm going to try to explain you our strategy. So we are a solar receiver provider, and we can provide also the heat exchanger on the ground, which make the link between the fluid in the receiver, the media in the receiver, and the steam in the power block in the steam cycle. We have these 2 products. And because this is a niche market, apart from this consolidation first strategical step of our products, we need to diversify our activities. And to do it, we have some opportunities in thermal storage because we learned a lot about thermal storage by developing, designing, manufacturing, and performing commissioning of these 2 products. So we are working hard on thermal energy storage, and we are working hard also on concept called Carnot batteries. Which is the idea to convert heat to power and power to heat after that. So you could imagine to forget CSP, forget the tower, and heat up directly electrically a fluid. And then this hot fluid, you store it. And when you need it, you use the power block to convert it in electricity again. So basically, this is a battery. It's absolutely a nonsense for a thermodynamic engineer, but it becomes profitable thanks to the developments performed in the CSP application. So basically here we are trying to develop a molten salt electrical heater. The molten salt is the main fluid we use in our technology. And this is a product which could be applied without solar receiver. Even if you do not have CSP, we will still be able to sell this kind of new product. This is why we want to develop it, because we are not sure yet that CSP will remain profitable in 5 or 10 years. We hope so, we think so, but we are not sure. So this is the second pillar of our strategy. We need to diversify our activity through thermal energy storage and molten salt electrical heater. And finally, we investigate also different aspects which could take a place in our future, meaning next generation of solar receiver, new media for thermal storage or CSP. Instead of salt, you could use solid particles. It could lead you to some advantage, such as to delete risk, such as the freezing. The salt can freeze, and if you are too cold, the salt becomes solid, and it's a nightmare in the design of our power plant to deal with freezing. Using solid particles, you avoid this risk, and you can also reach a higher temperature. Because if you are too high in temperature with salt, you will have more corrosion, for instance. But solid particles, of course, it's new. It's a completely different way to manage it. You do not have pump or valve anymore. You use some kind of solid transportation. So yeah, this is a challenge. The investigation pillar, we do it through thesis, subsidiary project, funded project, and stuff like that. So we put effort on it, but we do it through academical work and subsidies. Finally, it's not written here, but I wanted to mention that we are also involved to develop a supercritical CO2 cycle. Remember that in this that we have a power block with steam. We could imagine to replace this ranking cycle by a Brighton cycle using supercritical CO2. And theoretically, all the turbo machine should become smaller and less expensive. But when we speak with the biggest stakeholder in this area, they told us that they will be ready maybe between 5 or 10 years. So on our side, we are analyzing the heat exchanger, the solar receiver, the tanks, the piping, and everything to be ready. But this is, again, this is the third axis. And finally, hybridization. Actually, it's not directly in our strategy anymore because, as I mentioned before, we have a business unit which specifically make that to make the optimization of the different bricks which compose a John Cockerill solution. We have 15 development topics to follow this strategy. I'm not going to explain every one of them. I'm just saying that we have three levels of priority. And of course, the first axis, the consolidation of our product, is the first line here. And as you can see, lifetime and corrosion are two aspects very important for us. It's another view which can, yeah, okay, I will use it. I will repeat a bit myself in this line and the next one, but you will learn new information each time. So historically, the first generation we developed in 2012 was a water and steam solar receiver, meaning that we wanted to produce steam directly. So we sent the steam the water in the receiver, and then you produce steam, superheated steam, directly. The problem with this technology is that if you want to store it, you need drums, high pressure drums, and because this is high pressure technology, you have huge thickness of steel, and it costs a lot. So we had a project with about 3 hours of storage, something like that, in South Africa. Key Solar One was the first one, and after that, just for the little story, we arrived in the US with a new proposal with same kind of technology. Everything was the basic engineering was done, and we came back because they told us that no, they need storage. The market has moved, and our completely new technology was already old 2 years ago, 2 years after, so in 2014. So we had to develop a new technology based on molten salt. And it was the second generation of solar receiver. And we learned a lot about molten salt. We took everything we learned about solar energy, the aiming strategy, the mirror need to be focused on the right way. You need to take care of the hot spot on the solar receiver, etc. We learned about that, and we make a second transfer of technology from this direct steam generation to molten salt solar receiver. The first transfer was, as I mentioned at the very beginning, from the standard boiler to solar receiver. So first big project, BBB Bababa Viva Chile, Atacama 1. And it was great because it was partnership with the company in Spain, Abengoa, and it was the best years of our history because it was very challenging. It was amazing. We have developed completely new concept with them, and then they were in bankrupt, and so the project has been stopped during 2 years, and it has been restarted 2 years ago. Yeah, more than 2 years ago. Yeah, it has been stopped during 4 or 5 years, and it reborn 2 years ago, and now we are at the end of commissioning phase for this project. What I want to say regarding this slide is that you see that in blue we begin with the first generation, and then we develop molten salt. And we are currently, yeah, this is an old slide. We are in 2021. And actually, I'm quite proud because it was written that maybe we could have a new project, and we have it. We have just been awarded 2 months ago. But you see that we are at the end of the development of molten salt. We have done this development on projects through a funded project by by Belgium actually. We did internal R&D, of course, and we developed the solar receiver and the heat exchanger. And now we are analyzing. This is the third pillar, the investigation one, the solid particles one, and the gas phase one. And this is for our future. And again, we will do it through a funded project. The main targets we are following here are to increase the temperature. We need to reach 700 degrees C. We need to increase the efficiency of the system. We need to decrease the cost and increase the lifetime. This is the information below the slide. Just to know, you see my pointer or not?
Yeah,
actually?
yeah, we can see it. Yes.
Okay, perfect. Okay, so I have a few slides about the project after that, so I'm not going to spend too much time here, but I wanted to mention the different phases here. This is exhaustive. This is the complete list of the we are investigating right now. This one I'm gonna switch it, skip it. Okay, so it's another view to explain what the solar receiver is. I think I had a little video, maybe after that, but okay, you understood the main principle. You need to understand that we have an heliostat field which is out of our scope, but it's just to let you understand the order of magnitudes of about 3 kilometers of diameter around the tower, and you have just an idea of the size of a football field in comparison. One heliostat is about 150 square meters, so it's huge. We are speaking about something very huge. And regarding the receiver itself, because our equipment is the one on the top of the tower, it's on the tower, which is more than 200 meter height. So everything is complicated at this altitude. And in addition, we are in a desert, we have sand, we have wind, we have, of course, a lot of sun. And we have a very heavy equipment. It's about 2,000 tons. We have 40,000 tons of salt. And every square meter is absorbing more than 1 megawatt of power. And the salt itself, the molten salt, is heat up from 290 degrees to 565 degrees C. In addition to this high temperature, we have cycles, because every night we drain the receiver and every morning we filled up the receiver. So you have thermal cycle, meaning fatigue, and 565 degrees is the temperature of the salt, but the steel can reach 700 degrees C because of the amount of power, meaning that you will have, of course, creep and also corrosion in the internal side of the tubes. Basically, a solar receiver, this is an assembly of 16 panels of 74 tubes in the case of Atacama project in Chile, in a nickel alloy called 230. Sorry. So, and you have here the main dimension of this cylinder. Here, this is a very, very simplified PNID, but you see that the process is not so complicated. We have a cold tank on the ground out of our scope, a hot tank on the ground also out of our scope. And we pump the salt. We have buffer tank in our scope. We have panels in our scope. We have also an air tank and a balancing line. Of course, a lot of piping, as you can see on the ISO here. A lot of piping, a lot of valve instrumentation. Yeah, it's obviously not so simple, because also, as mentioned before, we need to deal with additional risk, such as freezing. So we need heat tracing everywhere to be sure that even by night, the steel remain hot to allow the filling in the morning. So a few words about each project. So South Africa, I mentioned it. This is the first generation. Chile, I spoke about it also. You see that on the picture. Now we have flux on this great receiver in Atacama Desert. And more recently, we had also a project in China and one in Dubai. And just 2 months ago, as I told you, we have a new project also in South Africa, same kind of project as the one we have in Dubai. I'm gonna try to maybe to share the video. Maybe I will need to. I shared. Yeah, I did a mistake. I shared not my screen. I shared the window. So maybe yeah, I will correct. Just tell me if you see.
Yes, now we can see the
Yeah.
Google Chrome. Yeah.
Okay, so it's an extract of our customer in Dubai, which is showing the construction of the tower. So out of our scope, but you will see at the end of the video also the way we lift actually the receiver, because everything is manufactured in workshop, and after that we erected everything on the ground. You see that they are beginning on the left here the receiver, the structure, and then when the receiver will be ready, we will lift it. We will lift the receiver in one piece through the tower. So okay, so this is the tower. Okay, so the structure in white is the receiver. Then you see the insulation. Then the black panel where they are painted in black to absorb power. Then we can erect everything in one piece. The 2,000 tons are erected in one piece, and this is exactly the same way we followed in Atacama project in Chile. Okay. So I go back to presentation. Okay. So this is just a few order of magnitudes. The one in Kisola one in South Africa and China were 50 megawatt electrical. And you see that the number of storage hours are impressive in comparison with PV plus ion batteries, lithium-ion batteries. You see that we are producing about 100 megawatt electrical on the two main projects here. But better than a long speech, a few pictures of the different projects. This is the one in China, the one in Dubai, the one in Cerro Dominador in Chile, and the one in South Africa. And this is the few first information of our new project. But basically, this is a 100 megawatt electrical power plant 24/7. Okay, let's talk about the challenges we have to design a solar receiver. So thermal cycling, I told you, gradient, because we need to, it's not a base load application. It was the idea at the beginning of the CSP adventure, but now they are willing to use CSP as a buffer because we have this storage capability. So they will, the owner of the plant to operate the plant by making multiple shutdown and startup and shutdown every day. So we have gradient, we have multiple thermal cycling, external solicitation as wind, sand, and of course, if a cloud appears in the sky, it means that the energy reflected by the heliostat, the mirrors will decrease that drastically very quickly. And then we have again gradient and again fatigue and etc. So I think that you get my point. We are in a very stressed configuration, and to design our solar receiver, we have defined different design criteria. I will give you a few words about it, but first I mentioned that a characteristic of our company is that we choose to remain independent. We have not the capability to manufacture and provide a heliostat field or tower. We are able to set up basically our solar receiver on every tower using every solar field. So it was a choice since the beginning to remain as flexible as possible. So train important criteria to make the design. So first we need to be flexible. I told you, multiple daily startup, wide range of operation, and they need we need to operate taking into account the moment of the day. We cannot choose the power available. This is just the DNI we have at 8 a.m. is not the same as the one we have at 12, of course. So we need to deal with it. We need to withstand high flux in static and dynamic state. Second pillar, we need something reliable. So the material selection is truly a key point of our know-how and expertise. We have developed also monitoring solution with digitalization solution to in real time to be sure that we are not going above mechanical limitation, thermomechanical limitation. So we have our own solution for that. We have optimized the limitation not to limit too much the heliostat field because it's also a nightmare for this guy to make the aiming strategy, because imagine this diameter of 3 kilometers of heliostat field on the ground, only to target the receiver, which is just a small point above a huge tower as this one. Of course, we need to impose some thermomechanical limitation, but we need to remain as reasonable as possible to let them operate on a flexible way as possible. And regarding operating costs, could be obvious, but it's related to the first line I show you. We are in a very competitive market. We need to be as cheap as possible. Donc everything need to be optimized in terms of limitation again, but also pressure drops for the pump consumption, and make the maintenance and the operation as easy as possible. To make the design, we developed 3 software. Just give you a few clues about each of these. Trying to go to next slide, but I don't know why. It seems that it's blocked. Okay.
Manuel?
Yeah, I'm still here, but apparently the slide I'm trying to share is blocking.
Manuel, when you talk about the cycles, do you consider only day and night, or also the clouds or the changes?
It's actually a very good question, because currently we consider actually 20,000 cycle of emergency defocus, because in some situation we need to defocus the heliostat field very quickly. If we detect, for instance, a hotspot on the map, and this is the most critical scenario. But actually, this is too conservative. But it's very complicated right now for our customer to define the cycles on a more optimized way. Ideally speaking, they should give us hot startup cycle, cold startup cycle, cloud cycle, emergency cycle, with a number cycle every time and hours of operation. And based on that, we will be able to make a new lifetime analysis to be more accurate. But currently, we are truly in this phase where every project we have are in commissioning actually. So we are learning, and they are learning also, and maybe they will come back with a split of cycles more defined in the coming months. This is the idea. But currently the design is based on just basically day and night, but with extreme gradients.
Yeah. And the software, you in John Cockerill, you also develop this software, or you are cooperating with Siemens or other companies?
In this case, we did it by ourselves. We did it by ourselves because it's truly related to our IP. And again, we are improving this software so much during the process. It's the heart of our technology, this tree software. So we needed to have it in our portfolio. So in a few words, the solar receiver design, SRD, is a steady state software. We use it to define the main dimension of our solar receiver and check the design criteria. So basically we use flux map provided by the heliostaphil provider. And based on this flux map, we can calculate the losses, the velocity everywhere, the mass flow, the temperature everywhere. And we will check, for instance, that we are not reaching too high velocity, that the internal bulk temperature will not be too high. If not, we will have corrosion, etc. So we use it mainly in proposal phase. And after that, of course, in the very beginning of the project, we need to validate everything based on that also. So first tool, yeah.
This solar receiver simulator also it also modulate like the dust of for the mirrors in the ground.
Yeah. Okay.
Like,
So the second one, you give me just the good link for the simulator. So first one, design, proposal phase, steady state application. Second one is a simulator. We use it mainly in project. It's a transient tool. And actually we can simulate almost everything we want. So it's like a digital twin of our solar receiver. And we can, for instance, apply, this is what is shown on the picture, a decrease of power provoked by a cloud, for instance, and see what will be the impact, for instance, on a buffer tank we have in the receiver. This is what you see in the picture. The power is decreased, and then the level control of the tank, the buffer tank, is active, and we see that we are able to maintain more or less the level, even if we have some kind of overshoot. So we will not simulate the heliostaphil because it's out of our scope. The heliostaphil provider have their own simulator, and sometimes they exchange information with us, and we use it as an input in our own software. This is the example I told you about the flux map. They can give us a flux map taking into account dust on the heliostats, maybe a cloudy condition, a cloudy day, or whatever, and they give us a flux map in normal condition and in dusty condition or cloudy condition, and we can run our software and make the comparison and see if everything is going well in static or in dynamic. I don't know if that answered to your question.
Yes. So the simulator is. What about like the accuracy of the simulations? Are very good, like comparing with the reality.
It's a physical model. It's a physical model. So of course, if there is something we have learned during the last 2 years, that there is a huge difference between the theory and the reality. So we are currently comparing this theoretical calculation and results with the one we have on site. But this is the link for the last software actually. But this is not so easy to assess the accuracy of the theory because the last has its own uncertainty. We know the uncertainty of the measurements of our monitoring system, more or less, but there is so many parameters that it's complicated to assess it very accurately. But for the moment, we have quite good match between what we have predicted and the reality for the main scenario we have analyzed. But you are right that uncertainty and accuracy is it's a challenge in this technology. The receiver monitoring, yeah.
And it's not an option like consider information from the LEO field, like because it's there is like a huge dependence between like the receiver and the information from the ground. So are you considering like to get information from the?
We choose to remain independent, and you are totally right that if we would have been how do you say that? If we would have been integrated, and if the Heliostar field would have been in our scope also, it would have been much more easier to make the interface. This is feasible to build in real time the flux map you apply based on theoretical calculation. When you know the position of each mirror, its orientation, maybe locally the DNI, if you have some PV cells on each heliostat, we are not able to do that because we did this choice to remain independent, but it's also what saved us because we have been able to work with different tower provider, different heliostat field provider. We are not just with one single one. And there is some company in the world who choose to integrate everything, but they are not the one which are selling most receiver right now. But you are completely right that this interface is a nightmare, and it would be very useful to have stronger link between both subsystems on site. But we have link. We have link, and the main one is the third software, the monitoring software, which is set up on site. So it's an operation software using in live to ensure the solar receiver integrity. So we have cameras on the ground, and we are rebuilding complete map of temperature of our solar receiver. And based on the temperature map, we can make a thermomechanical calculation, check strain, stress, corrosion risk, freezing risk, and we learn. This is a window to analyze in real time how works the solar receiver. And there is some link between this system and Heliostar field systems to help the Heliostar field to control everything.
So this thermographies kind of provide information about the main points like in the receiver, which are like, I don't know, associated with the, for example.
Yeah.
Like
so
it gives you like
what you see here
an address
on the picture.
Yeah.
Is for instance a preheating. So each rectangle is a panel. You have 16 panels. And you see that we are heating up the panels, we are doing the preheating, and we see in real time the temperature distribution at the external side of the tubes, of course. And then based on that, we can, thanks to a thermodynamical model, because we have also mass flow meter, thermocouple everywhere, metal temperature, salt temperature, etc. We can rebuild flux map, and we can rebuild for each cell, for each pixel, the strain and the stress and the freezing risk. So we have all the information for each point of the panels. And each cell is about 100 millimeter cross 100 millimeter. But we do it because we have this IR camera, infrared camera. The heliostat field provider can do it based on heliostat information, but we have no access to this information.
And the maintenance of these 16 tubes are your company is like your company is in charge of to I don't know, replace if
so
okay.
So no, our responsibility in the project is to design, manufacture, deliver the full receiver, supervise the erection, make the commissioning, supervise also the commissioning, and dealing with, of course, after sales. And the maintenance could be replacement of several parts, tubes or panels, and repainting, because, as I told you, we paint the panels to absorb as much power as we can. And regarding that, I wanted also to mention that we have developed our own coating, high temperature coating. So and we did that because we wanted to have everything in our hand to increase as much as possible the performances of the solar receiver. So this is a black paint, and the main advantage is that it's a paint you don't need to cure. The main coating on the market need to be cured. So you perform a curing to stabilize the coating, and it's okay in a workshop, but then when you have to do it on site, it's complicated. So this is something I wanted to mention, and also a word about the lifetime. To make the lifetime analysis, I spoke about the cycles and so on. We need accurate model of the materials. We have not so many materials actually. We have the nickel thalloid and a bit stainless steel, 347H, and also a bit of carbon steel. And for the alloy 230, which is the material we use for the tubes, we have developed our own constitutive model. So it's a model of the material developed by making a lot of different tests and even fatigue and creep tests with molten salt in the tube. And at the end of these 3 years developments, we have now a model we can use in software such as ANSYS to take into account the real behavior of our material. This is from a mechanical point of view, and regarding corrosion, we have designed and manufactured a test loop actually. A test bench to test the impact of corrosion on the tubes and to take it into account in the lifetime model actually. So we have stage which is starting right now to improve the constitutive model to take into account also the corrosion of the alloy 230.
One minute, a question.
Yeah.
With the information that you handle now, the corrosion is mainly because the alloys used, or mainly
Due to
for
the
mold? What is the proportion in the behavior of each case for molten in certain percentage, or for the metals alloys that can produce electrolysis or electrolytics behaviors.
Yeah. To be honest, I'm not a chemist myself, and what I can say is that actually the alloy 230 is the most noble material we could choose in this area. So we had no option. The molten salt has been imposed. It's a solar salt. It's the most common in this kind of technology. So we cannot choose the salt, and the material itself is the most expensive we can buy. So I'm not sure I get completely your question. You are asking what if the corrosion is provoked by the salt or the steel itself? This is the question.
Oh, yeah, yeah.
I'm not sure to get it. Yes, this is that.
Yes.
Yeah. So I cannot answer properly, but definitely the salt itself at about 600 degrees C phase to degradation, and we have impurities and we have degradation of the salt locally, which could lead to corrosion.
Yeah, and actually, do you use or sorry, actually you in the plant you are using inhibitors of corrosion to the process?
No. But we are analyzing that in the frame of this project. So the loop has been developed in the frame of funded project by Belgium, partially with partial subsidies, and one goal is to take into account corrosion in the constitutive model. Another goal is to develop inhibitive solution and anti-corrosion coating. So we will investigate it, and we are also analyzing other kind of salt, even in nuclear application where they are using inhibitors also. But for solar salt, they are not using it. I don't think so. And we are not buying it actually.
Okay, you make the point. I was to propose the solutions used in the nuclear plants with the corrosion issues.
Yeah. We are aware, but we are not investigating that in this application. But anyway, the salt itself it's not in our scope actually. It's as I mentioned, this is a constraint and we have to deal with it. But so there is no inhibitors. It's a pure mix between KNO3 and NiNO3. Yeah.
Manuel?
Sorry?
No. I have another question, so you can finish.
Okay, maybe just to conclude, I wanted to tell you that the salt itself can face to degradation above 600 degrees C, and I told you that we are not reaching this value because we stop at 565. The problem is that because we have 1 megawatt per square meter, we have 700 degrees C at the external phase, and we can reach 650 degrees C at the internal phase of the tube because of the bulk temperature. So typically here, this is a limitation we have to monitor. So thanks to the monitoring software, we recalculate this internal temperature, and we have to limit the absorbed flux. They have to defocus partially the Deliosta field to avoid to reach this value. If not, we have this degradation of the salt, and then we have corrosion. And typically there is something to optimize. If we could prove thanks to this test bench, that we can increase this limitation of 10 degrees C, at the end of the day, it could save millions to the final user in terms of electricity production. This is why this test bench is very important for us. Please go ahead with your question.
Yes, in an average way, how often do you replace one of these nickel alloy tubes, like for maintenance?
Yeah. Okay.
Mm-hmm.
This is a good question. Theoretically, you don't need to replace it. But again, it's purely theoretical. Something very amazing with our technology is that we skip all the pilot and test bench step, and we go through industrial application and large scale directly, meaning that everything has been done from a theoretical point of view. So I will not be surprised that we would have to replace some parts in a few years, but we will see. But from a theoretical point of view, for 35 years, in the case of Atacama project, we should be good. If you do not face to a critical scenario, and there is typically one critical scenario you could face, which is freezing in your solar receiver. And if you face to freezing, you could induce a difference of temperature between tubes, because you will have one tube with a solid salt and one tube cool it down by molten salt. And so you will have one cold tube and one hot tube. And the difference between these two tubes will induce thermomechanical stress in the branch, because the tubes are connected together by headers, big pipe on the top and the bottom of each panels. So you have branches, you have what we call nozzles, and they have their own flexibility. But if the unbalanced temperature between two tubes is too high, you can bend it. And this is typically a scenario which should be, again, if I can take the comparison with the nuclear application, it's the nuclear incident of CSP application. Freezing, you need to avoid it in any way.
Yeah, like a critical scenario, like the worst.
Yeah, but in the reality, to be honest, you face it, so you have to deal with it. And again, this is something on which we have learned a lot, and we can manage it now. We are able to perform what we call thawing and freezing, but you need to do it very, very carefully. We have improved the algorithm in the monitoring system to take it into account, etc.
Manuel?
Yeah.
So here you have a constitutive model, and I think maybe one of the key parameters of your design is the thickness of the tube, but maybe you have one thickness or different thickness for or different applications or different power tower, or how do you deal with the models to compute strain and the cycle?
Okay, yeah, understood. Okay, again, a good question. Just I take the opportunity to give you just one more clue about your last question, the cycle. Every morning before filling, we need to preheat the panels. As I mentioned, all the piping and tanks, etc., are heat traced, so it's easy. We can electrically heat trace everything. But the panels themselves, we need to make the preheating every morning with using the heliostat filter. And then when you reach 300 degrees C, you can make the filling with the salt. And actually there is two interesting facts. First, because you do not have salt in the tube during preheating, it's very complicated to reach an homogeneous temperature map. So meaning that you will have 300 degrees C somewhere, it's the minimum value to fill up, and somewhere else you will have, I don't know, 500 degrees C. Meaning that if you make the filling there, you are at 500 degrees C, you will cool it down at 300 degrees C during filling, and after that you will heat it up again to reach the final temperature. So every morning you have an additional cycle. If you do not do the aiming strategy and the focus properly. And again, this is something we discovered in the reality. We had an idea about that, but you really face it during the beginning of commissioning. So additional cycles there, and also a printing very complicated to perform because you do not have inertia, you do not have salt, so you will have temperature imbalance as the one you have with freezing. It could be induced by the wind, and you are not able to compensate the losses you have locally in a corner, for instance, by using heliostat of 150 megawatt square meters. They are too high. You have a big light spot on your solar receiver. If you have just one cold tube, you cannot reach the permissive, the minimum value in this area, and maybe in somewhere else, just next to this tube, you are too hot. So it's very complicated. Okay, regarding your question, actually, we try as much as we can to keep our design as constant as possible for the panels, at least, for what we call the lighting area. So the parts of the panel which are exposed to the flux. So we keep, till now, for all the project, we maintain the thickness and the diameter. So we are good for the constitutive model. And indeed, it took us years to develop the model. So if we change something there, we will be in trouble. Definitely.
Thank you.
No answer, so I guess yes.
Yeah, thank you, Manuel. And yeah.
Okay, I go ahead. So next slide is just I don't know if you know this sentence, but in French we say that CFD is color for director. So nice picture, nice sketch, just to tell you that we are doing hundreds of simulation. On the left you have pre-heating simulation. It's all the simulation we do it internally for the same reason we developed the software internally. It's the heart of our know-how. So you see the preheating. You see also that actually you have a maximum temperature on the crest of the tubes because the profile of the flux is kind of sinus. And because it's also another interesting fact, with the monitoring, we have a pixel of 100 millimeter, one tube is 50 millimeter. So one pixel take two tubes. So you cannot catch the maximum temperature on the tube crest. And actually this maximum could be 50 degrees more than the average value on the half tube. So we need analytically to calculate this maximum temperature on the tube crest. And again, we have performed this job analytically and based on CFD calculation and so on. And now we are validating all this model, all this theoretical model. So same kind of comment as the one I gave you regarding uncertainty on the simulator. We are currently trying to calibrate everything and to make everything matching. Second illustration is a freezing simulation. Basically, it's very complicated to monitor it because you will freeze from the outside to the center of the tube. The good news that you will have a channel empty on the center of the tube to let the salt pass till the very end of the freezing process. So it lets you an opportunity to trying to reverse the phenomena by introducing hot salt or whatever, or increasing the speed, trying to provoke erosion and stuff like that. But the bad news is that you are blind, because when solid phase appear, the temperature of the tubes will remain constant. And on the other hand, you don't know when you have reached the thawing, the unfreeze. It's complicated. We found some solution, but it's not easy to detect freezing and to detect the unfreeze tube. The last on the right is a filling. You should know that after preheating, the filling phase is very critical. You need to do it very quickly because there is a huge risk of freezing. You need to be sure that the pump are in good health, and once you begin, you finished. And after that, you begin to circulate everything. And here you have a study we performed specifically to analyze local effects of the winds in the corner to understand what kind of unbalanced temperature we could have between two tubes. Again, a lot of simulation, but also a real small scale part of our solar receiver. You see several tubes and a corner, and we used it in a wind tunnel in the University of Liège in Belgium. I have two slides just to show you real map of one of our solar receiver, just to let you understand what we see on the screen and what do we learn about it. So first, the preheating. You see it's not homogeneous. You have 400 degrees C somewhere, and you could have maybe 240 somewhere else. And at the end of this process, you need to reach the minimum value everywhere to perform the filling. So a very challenging phase because you need to be very careful because there is no inertia. And in addition, you need to be very quick because every minute is money. The advantage of our technology is that we do not have fuel. It's renewable energy. The sun is available. But of course, there is a business model behind that and a PPA to sell electricity. And the performance model has been based on the fact that we need to perform the preheating in very short and limited time. So it's a big challenge to achieve this preheating duration. Then we fill the receiver, and you see that there is a line of the front of the salt, so we can detect actually the filling. We have developed since the beginning of the commissioning a new feature to our algorithm to detect this front and evaluate the level of salt in the panels, which is a parameter which could be useful in several manners, but I'm not going too much into details. Then you see also that we are filling everything in parallel, every 16 panels in parallel. And after that, we need to switch to power mode as quick as possible because we will have a very short mode, not shown here, which is the static mode. We will have during maybe 1 or 2 minutes salt, liquid salt, molten salt, but static. And then we need to activate the proper valve to make the two circuits available to circulate salt. And this is what you see here. The two inlet panels are the 12 and the 13 one, and the two outlet panels are the 4 and the 5. And you see that right now we are increasing the temperature, but we go from 300 to 420 degrees. And at the end of the day, we need to drain, and we maintain flux to be sure that we do not have freezing anywhere. But as you see, during drainage, we still have the thermal inertia, and everything is homogeneous. It's much more easy to manage than preheating. And in addition, the time doesn't count anymore because this is the end of the day. The second slide is even better, I think, because you will have a look on not normal situation. And typically, you see that here we had some salt introduced by the top of the panels, and the panels weren't preheated. And because of that, we had some freezing, and that you can see it on the next picture, because when we tried to perform the next preheating, we realized that the thermal signature of our solar receiver was different somewhere. We had some discrepancy on the panels 12 and 13. So we had 2 tubes frozen, sorry. And even in power mode, you see it. So this is bad. And what you need to do is a towing procedure. So we developed a kind of preheating mode, but with specific way to make the focus, beginning by the bottom and go to the top, because you should know that if you, well, you know that if we melt ice, well, the ice take more volume than water. And actually, this is exactly the opposite with salt. So if you melt a plug in the middle of the tube, you will crack it. So one way to avoid that is to focus first the bottom and then go to the top. And well, this is one of the features we had to follow in this towing sequence.
And what is the way that you use to defrost it?
So the 2 main way are the kind of preheating. So we will focus using the heliostat field. We will, as I mentioned, begin by the bottom and go to the top, focusing more and more mirrors, but be sure that we melt everything on the bottom before going to the top. And at the end of the process, it's like a preheating. Everything is hot. And we do it using a thermomechanical limitation in the monitoring software lower than the one we used in normal preheating. And if it's if the towing takes 4 hours, we don't care. It's not a preheating.
And
so
you
this
use
is the first method.
Yeah, and you start to defrost it like at the beginning of the day or during the day?
Well, again, this is a nuclear incident. So if we have a freezing, it's absolutely not frequent. First, we think, we analyze, we try to understand why we had this kind of scenario. We hope that at the end of the commissioning, we will not face any kind of freezing. And what basically you need to do it when you have energy. So we need to avoid to do it at the end of the day. You need to do it when you know what occurs and you do it on the middle of the day, for instance. Then you have energy. You begin by focusing 1, 2, 4, 6 mirrors, and step by step you continue.
Okay.
And you monitor everything very carefully. And the second way to make the towing is to go to power mode. So at the end of this long preheating and very careful preheating, you could reach a more or less homogeneous map and hope that you are good. And then you switch to power mode. And this is what occurs there. But as you see, the frozen tube on the panel 13 disappears, but we still had some frozen tube on the 12th one. And we decided to operate in power mode as long as we could. And we asked the heliostat field power provider to give more power to the panel 12 step by step, monitoring very carefully the thermomechanical value on this panel specifically. Well, it's a simple way to explain it, but basically this is it. We use the same mode, but we pay attention to the frozen tubes and we pay attention to the heliostat field which we decide, well, the heliostat we choose to focus, and the sequence we follow. This is a slide to show the local phenomena in the corner. So I explained before, but you have wind. This is what it's shown in this view. You have non-homogeneous losses, and you have an homogeneous flux because the heliostats are huge, meaning that you have non-homogeneous temperature, you have temperature imbalance, and you have thermomechanical risk. So there are plenty of manner to optimize that, and we are working on it. You can improve the monitoring. You can optimize the thermomechanical limitation. You can work with the heliostat field provider to optimize the mean strategy when you face to wind, etc. And what we did also is to build a CFD model of our solar receiver, but we did that. We just finished this job. It's the most advanced CFD model we ever done on the last 10 years. We have modelized everything, meaning the panels, the steel structure behind the panels, which support the panels, the insulation behind the panels, the gap between each tubes, the thermal shield on the top and on the bottom. You see that we have insulation. This is thermal shield, the tower itself, and we are able to, on a very accurate way, to evaluate the infiltration into the tubes, the infiltration behind the panel, and evaluate the temperature all around each tubes. And we are comparing right now the theoretical results again with reality. This phenomena, again, even if we had some clue about it before commissioning, we deal with it right now. Every day is a discovery. Okay. So it's just a slide to summarize that basically our design to deal with all this risk use the tree software, and all the process is fed up by the lesson learned from the different sites, the test bench, the wind tunnel test bench we did, simulation, the constitutive model, etc. In conclusion, regarding the market for solar receiver, it's a complex technology. It's expensive. We cannot build it everywhere in the world. But we see that there is a market. And historically, it has been supported by specific policies, meaning that in the past it was Spain and US, and after that it has been China. Currently, there is a major stakeholder in North Africa, and we see that there is some opportunities. There is some opportunities in place like in Chile, actually, but also in Australia, in South Africa. So we will go ahead and we will continue to consider our strategy and our technology and trying to convince everybody that it's working. And yeah, well, this is what's written here. We need operational references. This is what we are working on. We need to consolidate and optimize our product and diversify our activity. I have, just to conclude about the solar receiver, a few pictures about Cerro Dominador, extracted from LinkedIn of CED, which is our final customer. And cherry on the cake, a few pictures by night, less flux, but a good picture of the receiver. I'm just having a look. It's already 10:30. It's okay if it's up to you. I can spend a bit more time with you. To be honest, I think that I have still the same number of slides I've already presented to you. But the reason is that the next slide were about the next axis of our strategy. So I think that you had a good overview of our main product, which is the solar receiver. you know that we are also active in the heat exchanger on the ground, which is making the link between the molten salt and the steam power block. We have this product also, and that we are investigating a new kind of product, new fluid, new type of solar receiver. I think that it will be for another time, another story. Maybe just going very quickly on a few pictures of the heat exchanger. It's a shell and tube design, and we developed it specifically for molten salt application because we have learned that this is a critical component which has leakage on the CSP plants existing around the world because they are using traditional shell and tubes instead of specific heat exchangers. And just to mention one fact, there are connection between the tubes and the tube sheet, such as this one, expanded tubes, and this is absolutely not suitable for such high level of temperature because if you do not use welded connection as the one we propose, you will have locally creep and cracks, and then you have leakage. So we developed a way to make this connection with a butt weld full penetration connection, and this is one of the main features of our heat exchanger. And the second main feature is an helical baffle instead of standard baffle, which make the consumption of the pumps lower and improve the heat exchange. Okay, this I just skip it. I wanted to give you just a view of our test bench. It will be in a container, and basically it looks like that. So it's a loop molten salt, and we reproduce the filling and drainage of a solar receiver. We reproduce the temperature gradient, temperature level. We will test all the instrumentation we have on site. We have an induction heater to simulate solar flux, and it has been very challenging to be able to reach 1 megawatt per square meter to generate this gradient in the thickness of 50 degrees C between the internal and external side of the tube, and also a challenge to monitor the inside temperature of the tube because this is the temperature we monitor regarding corrosion. And we did it through an analytical calculation calibrated on some real tests. So this is a molten salt loop. So we heat up the salt, then we cool it down in this heat exchanger and go back to a hot pot. And of course, we have a PLC control everything. And we have different partnership with valve and instrumentation provider to test this kind of instrumentation, discuss this kind of equipment and materials in contact with salt. And we have, apart from anti-corrosion coating and inhibitors, the project to test new salt, new materials in the second campaign of test. And so this is also typically something where there is space to academic job. And this is also why I wanted to just to emphasize a bit more this test bench. We have currently also a new opportunity to make a conceptual design for a molten salt test loop, but not for us this time, but for a nuclear application in a small modular reactor application. I don't know if you are familiar with it, but if you are interested by this new kind of nuclear reactor called small modular reactor, have a look. It's interesting. Yeah, that's it. Very quickly, we designing new kind of solar receiver using air instead of salt, using particle instead of air. We are involved in a European project here at a pasta factory in Italy, and we develop a heat exchanger, particle on one side and steam on the other side. So it's a very good way to learn about particle, but we are not yet involved in solar for this project. Here you have just an idea of what look like an heat exchanger with a particle instead of salt, using a particle. And also we have a second European project investigating a supercritical particle heat exchanger, a supercritical CO2, sorry. And I'm done. That's it. I don't know if you want to ask me more questions, or if you have any comments, I would be pleased to give you more information.
For sure, there will be. Thank you very much, Manuel, for your presentation and for sharing this precious information for your company, because of course it's not really easy to have this kind of knowledge share in a classroom or with common students. But yeah,
it was a pleasure. I hope it was appropriated. I wasn't completely sure. I get the specific description of what I should present. So, do you think it was appropriate?
Yeah, I think was great. I think we have a lot of we have a lot of subject to for research, for cooperate with you, of course, and if maybe one of the students is interested in the future, as we discussed, of course there are options in Université de Liège, in John Cockerill, maybe yes also, and
clearly,
yeah, the student have to spend 2 years in the industry in one company mainly to develop their master's thesis, sorry, their PhD thesis. So
yeah,
that's an opportunity.
Yeah. We are familiar with it. We used to have between 2 and 3 students everywhere every year. Usually they are finishing their engineering studies, but sometimes it's also a PhD, so it makes sense. And we have a lot of subjects related to to materials, corrosion, and optimization of heat exchanges and stuff like that. So yeah, you are more than welcome. If something in the presentation make you dream, please come back and ask.
Yeah, thank you very much. Maybe you can ask some questions if you have some questions for the students.
Some additional one.
Additional ones, yes. Or
I have a question, but I wait for a student first. Thank you very much, said Felipe. Manu, thank you very much for your great project. Very, very interesting. I have a question, not technical. I would like to know, taking in account our program. I don't know if Victor tell you detail about this. Sorry. Program. I would like to know your opinion on if, for example, have formal relation with the university, connection with the University of Liège. How is this relation with PhD student? How you consider have some PhD student in your company? In all projects, you show a lot of things in simulation, in experimental tests. Everything is carried out for you in your company. Some part is in university, some research project, research institute. Can you talk about this topic?
Yeah, absolutely. Yeah, we have a lot of connection with the U of Liège and the CRM also, which you may know. And for instance, the constitutive model has been developed in partnership with the university. So this was a major project for us, and for instance, there it has been performed with the university, and we are also working with them with different master theses related to our third pillar investigation. for particles and supercritical CO2. But generally speaking, there is no barrier. You can reach us through the University of Liège, or if you want to come to us in direct, it's feasible also. We do the both, and we have also connection with other universities. So it's completely in our spirit to make this some jobs jointly, avec some work jointly with academics. So yeah, and there are some simulation we performed with the university also, and some other research center. So yeah, feel free to imagine some framework, and we speak about it.
Perfect. Thank you very much, Manu.
You're welcome.
Okay. I think we have a great time with Manuel, and of course, Manuel, if next time we can have a meeting or another presentation. Yeah.
If you have any additional questions, please revert.
Yeah.
My pleasure. Maybe because it's 10:30 here, I need to prove to my boss that I've been working today. So if some of you can just share your camera just a minute, I would be glad to see your face.
Hey, I don't know why today nobody is with camera.
Okay.
We can take a picture.
In this case, if I have no additional face on the screen, I will just share your both faces to my boss, and then I'm sure he will be very happy with that.
Yeah. But if the student want to share the camera to take a picture, maybe no. Or
it was the idea.
Yeah, or
Yeah, or
yeah. So here we go.
Picture.
Okay. I think it's
okay. It will be a picture of you, Victor. Sorry.
Wait a minute.
I'll
Take a minute, man.
Facebook profile.
I want
No.
How do you put the gallery? Ah oui, affichage, gallery. I have it. Okay. Great. Okay. They are coming. Nice to meet you. Encantado.
Thank you very much, Manuel, and
thank you.
Say hi to your colleagues and friends in Belgium, and hope everything is going to be better these hard days.
So.
Yeah.
Hope so.
Yeah.
Okay.
Thank you very much.
Thank you.
A big pleasure. See you again, Manu. About a long time.
Bye bye. Thank you.
Bye.
Genial. ¿Cómo estuvo la presentación? ¿Le gustó? A mí me encanta.
Tuvieron tímidos hoy día, encontré, profesor.
Sí, que bueno, igual es fácil seguir, me imagino, seguir todo ese lenguaje técnico y todos los problemas que tienen. Hay cosas muy del área mecánica y bueno, depende de la especialidad, pero yo creo que como todos tenían la información de la presentación, ya por lo menos habían investigado algo. Esa era mi idea, que se prepararan para poder tomar nota más, de forma más eficiente, pero de todas formas van a tener grabada la presentación. Esta sí se va a subir de forma oportuna para que puedan preparar sus trabajos, y si es que no alcanza todavía el tiempo. Y bueno, esta presentación apareció así de la nada porque había una opción, había un espacio y justo estuvo el contacto ahí disponible para compartir, pero realmente la empresa Cockerill hace cosas bastante interesantes. Hay muchas empresas del área tecnológica que colaboran bastante con la universidad. Y eso es porque la naturaleza de las empresas es desarrollo, ingeniería, desarrollo, construcción o manufactura. Y claro, ellos necesitan de la universidad y la universidad necesita de ellos, porque están formando estudiantes que luego trabajan en esa empresa, entonces es lógico. Pero es interesante, y la opción, Manuel decía, Gonzalo, decía que, bueno, está abierto a la postulación de proyectos, lógicamente, está abierto a recibir estudiantes, en la Universidad de Lieja igual, con la directora de investigación también, ahí tenemos un convenio de colaboración internacional con con la UFRO, pero igual se puede expandir a la macrofacultad, en realidad no hay restricciones. Así que...
Sí, yo dejaría la invitación abierta, no es una oportunidad menor. La Universidad de Lieja es una gran universidad, ¿cierto? Y son contactos que pueden usarse en forma permanente, en cotutela, en pasantía, ¿cierto? Y aprovecharlo a medida que se pueda. Sirven, son una experiencia. Yo tengo un estudiante de doctorado que está terminando y por la pandemia no ha tenido ni una chance ni de ir a un congreso, entonces creo que dejar una instancia como esta con algo faltante, así que yo no descartaría para los que están acá tomar estas oportunidades que a veces pasan ahí como así, estamos disponibles y nadie las toma, ¿cierto? Un doctorado por lo menos yo creo que requiere una pasantía, así en el peor de los casos.
No,
Hay que aprovechar esas chances.
Y la Universidad de Lieja y en la ciudad de Lieja se pasa bien, ¿cierto, Gonzalo?
Sí, es muy bonito. Ahora está todo inundado así, pero es muy bonita. No, Bélgica en general es súper entretenido y todo, así que está recomendado aquí por sus dos profesores presentes.
Sí, no sé si bueno, alguna apreciación, algún comentario, si alguien quiere...
Sí, yo tengo unos profesores. Más que nada respecto a la problemática de como abordadas a lo largo de la presentación. O sea, él hizo harto hincapié en que todo se modelaba con componentes teóricas y después ellos lo aplicaban a la práctica y no siempre había un match ahí entre dada lo específico del tema, dado que tampoco hay muchas plantas solares ni empresas que se dedican a hacer estos tipos de, perdón, como receptores solares, como para conectarse a matrices de energía. Entonces, respecto a lo que uno pueda encontrar en la revisión bibliográfica que hay que hacer, tipo, no creo que haya mucho referente a lo mismo, entonces, ¿cómo lo podemos hacer ahí?
No, sí
Eh,
hay bastante. O sea, a ver, el Manuel enfocó varios temas, se enfocó a varios temas, habló de creep, fatiga, corrosión en el alloy, en la aleación 230. Entonces ahí hay...
claro, pero lo que voy es como, así como podría vincularse algo como, o sea, no directamente con este problema como tal, sino que quizás hacer un análisis como de ese material, por ejemplo, pero abordado en otra industria, quizás, ¿no?
Claro.
¿Se puede orientar por ahí?
Sí, o sea, la ideal es que, por ejemplo, nosotros con la Universidad de Lieja, yo tengo un artículo con esta universidad y trabajamos en este tema hace ya bastantes años, o sea, llevamos, ¿cuánto? 5 años aproximadamente. O sea, hay un artículo, pero la idea es que no todos busquen ese. Y en ese artículo se abordó un aspecto de la problemática, pero más enfocado al software, a la implementación del modelo constitutivo, a los cambios de temperatura y que no siempre los datos se tienen de forma continua, sino que hay datos discretizados a ciertos niveles y cuando uno cambia de un punto a otro, los software a veces no convergen, entonces ahí hay una estrategia, pero hay bastantes artículos. Nosotros en la UFRO igual hemos hecho trabajos de pregrado, y hay mucha investigación. O sea, no es la única empresa en el mundo que está trabajando en esto y no es la única universidad. En Europa hay varias universidades que están con este tema porque es un tema interesante. O sea, producción de energía limpia y además que tiene muchos desafíos para aumentar la eficiencia. Entonces, tienen que llegar a temperaturas más elevadas, la aleación no logra llegar a esa temperatura o tienen que trabajar con recubrimiento. Hay artículos, un montón de artículos, pero lo importante es que busquen quizás con las palabras claves, pero ahí en la presentación aparecían en inglés. O sea, tienen CSP Receiver, tienen Heat Exchanger, tienen Molten Salt, High Corrosion, Creep. Bueno, quizás eso son cosas un poco más mecánicas, pero me imagino que todos las conocen desde los cursos básicos de materiales. Corrosion, Creep y fatiga. Entonces, yo creo que traten de hacer una búsqueda y con esas palabras clave, y si no encuentran nada, la verdad, bueno, podrían desviarse un poco, pero yo creo que...
Yo creo, Víctor, yo creo que la pregunta va por otro lado, que corrosión tú pones corrosión y te van a tener 100 millones de artículos de corrosión. El tema es si es que la búsqueda tiene que ser exclusivamente, por ejemplo, en corrosión en paneles colectores solares. Entonces,
Claro, exacto.
yo creo que esto puede ser más amplio porque la problemática de la corrosión en el material, por ejemplo, que él mismo dictó, va a encontrar un montón. Probablemente sí más acotado en este problema en particular, pero para estudiar corrosión, por ejemplo, de que va a tener información para eso, va a haber. Yo creo que la pregunta era esa, si tenía que ser exclusivamente enfocado en el problema que presentó Manuel hoy día. Yo creo que no. Yo creo que puede haber igual información, sí, Felipe, pero en forma genérica, todos los conceptos que hoy día se presentaron son muy, muy conocidos.
Pero
No, sí, era exactamente el tema.
Vale, perfecto.
Me refiero a que tienen que acotarlo a, o sea, probablemente muchas veces uno publica resultados y no lo asocia a una empresa, ni lo asocia.
Claro, a eso va la pregunta. No. Va a encontrar información, probablemente no la gran mayoría a esta problemática en particular de hoy día, pero la problemática es transversal, así que sí, en ese sentido yo creo que no hay ningún problema en que la búsqueda sea así por genérica, por decirlo.
Por ejemplo, no van a buscar corrosión con ácido sulfúrico, o sea, tiene que ser corrosión y sale fundida. O sea, hay muchos artículos, hay muchos centros de investigación, hay centros de Estados Unidos, pero yo creo que hagan la búsqueda. Si no encuentran en 2 horas, me envían un correo y yo les puedo enviar algunos links, incluso hay desafíos. Global Challenges of CSP de corrosión. Entonces hay un grupo de investigación enorme en el mundo que está trabajando y que está colaborando, los laboratorios de NACE, o sea, hay un grupo enorme, yo creo que van a encontrar. Pero traten de enfocarse a los problemas que él mencionaba, o sea, corrosión, pero con sales fundidas, fatiga, con ciertos números de ciclos, con los rangos de temperatura también, o sea, porque si buscan corrosión a temperatura ambiente, es un mundo enorme, la corrosión es un mundo enorme que vamos a escuchar cosas que quizás no interesan mucho a esta área de la empresa. Y la idea es que ustedes formen algo, se preparen ahora o tengan un poco de conocimiento si es que más adelante aparece alguna opción o alguien se interesa. Nos sirve a todos, yo creo. Hagan el esfuerzo, pero igual no lo acoten, como pensaban, algo tan específico, ¿no? Creo yo, no sé. Bueno, ¿qué crees tú, Gonzalo?
Sí, es que yo creo que va, sí, yo creo que la pregunta del Felipe es súper acota. Si no tiene para qué llevar el apellido de paneles recolectores solares, tiene que llevar el apellido de, por ejemplo, corrosión con fundición de sales o esto. Pero en paneles, por ejemplo, ya esa parte creo que se puede obviar si es que no encuentran. De pronto sería yo no he buscado personalmente, no es mi área, no lo he buscado, pero creo que esa es la subbúsqueda que les va a entregar resultados seguros.
No, sí hay información, sí, de los trabajos que hemos hecho, o sea, hay harto. Basta encontrar un paper y ahí uno después encuentra todas las otras referencias que vienen detrás. Ahora, sí, quizás hay otras problemáticas que Manuel podría haber presentado para hacerlo un poco más amplio, pero bueno, no tuvimos el tiempo y ya estaba cansado, 10:30, bastante tarde, después de un día de trabajo. Eso. Hoy día teníamos alguna presentación, algún trabajo.
Sí, lo que sí estoy perdido si le toca a los 2 grupos o a uno solo. Así que vamos a pedir a los mismos que nos digan.
Que hubieron 2 semanas sin presentaciones. Como que quedó un grupo único pendiente y después los de la otra semana 2 grupos pendientes también, creo.
Sí, yo creo, Víctor, que vamos a tener que además ver un tema, porque ahora como se dio el desfase de los 15 días, nos va a empezar a pillar el fin de semestre, donde van a haber charlas que o las volvemos a evaluar juntas o dejamos charlas sin presentaciones, por ejemplo, que ya serían como van quedando las últimas 2 charlas, si mal no recuerdo, así que vamos a tener que ver eso también.
Sí, porque igual es bastante carga para todos, para el que revisa y para el que evalúa. O sea, para el que desarrolla el trabajo y el que evalúa. Vamos viendo, entonces hoy día son las 5. Tenemos hasta las 6:30, yo creo, ¿no? 6:30 aproximadamente.
Son cortitas las presentaciones.
Podemos tener un break
son de 7 minutos.
de 10 minutos, por lo menos. ya que llevamos 2 horas sentados, 10 minutos y volvemos para las presentaciones. ¿Les parece?
Sí.
Sí.
Sí. Profe,
Sí.
me
Carlos.
quería hacer una consulta, no importa que los demás chicos vayan a descansar si respecto a la tarea que subimos. Lo que pasa es que yo se la envié el domingo antes pasado, porque no pillé el link en el campus, entonces ahora me metí y yo había puesto la tarea hasta ayer, pero yo se la envié al correo. Igual la subí ahora, pero quedó como atrasada. Entonces, más que nada para avisarle que la
Sí,
que
no,
subí-
igual,
¿Me está
profe.
hablando a mí, cierto, Carlos?
Sí, pues se la envié al profe Gonzalo. No me acuerdo si he copiado al profe Víctor, pero...
Parece que iba yo solo. Por eso a lo que le respondí, que fue creo que fue a Marion también, que me pasó lo mismo. Aunque se cree tarde la entrega, súbanla ahí porque, como le digo, a veces les toca a otro profesor corregirlo. Entonces me la mandan a mí solamente, pero le toca a otro profesor. Pero por el
Ya.
tiempo de entrega no hay problema, no se preocupen. En ninguno de los casos que me han mandado Felipe, Jorge, Marion y tú, creo, mail. Preocúpense después de subirlo a la plataforma nomás, pero no hay problema por el tiempo de entrega.
Okay. Yo por lo menos no lo había visto y lo subí ahora hace un ratito nomás. Pero eso.
Vale, no hay problema, ningún problema.
Sí, vale, gracias.
Profe, Gonzalo.
Sí.
Sí, nosotros expusimos la semana pasada con el decano. Estaba...
La última anterior, sí. Ahora faltarían
Sí.
los 2 grupos entonces, los
Sí,
que
sí.
quedaron pendientes. Ya.
Vamos
Es que-
nosotros con Quillay Surlat.
¿Cómo?
¿Cómo?
Vamos ahora nosotros con Quillay Surlat. Con
Sí.
esa-
Pero van los 2 grupos, los 2 grupos. Estamos con 2 grupos y un grupo alternando, ¿no? Hoy día
Sí,
le
sí.
toca a los 2 grupos. Ya, sí,
Sí,
tenía
por eso-
razón Marcela, me acordé.
Por eso te comentaba, porque nosotros estamos preparando la charla para la próxima semana.
Sí. Ahora me aclaré. Estaba un poco confundido. Sí, ahora gracias por recordar, ahora quedé clarito.
Vale, gracias.
Gracias.
Gracias a ti.
Ya, a descansar unos minutitos.